Thanks. So this is like a brief introduction about how we can constrain the photonal coupling with high energy astrophysics, and I will span from radio up to high energy gamma rays. So what is the landscape for Axion ALP-photon coupling? You have probably seen that already yesterday, but we have actually a very broad range, not only in mass but also in coupling, that can be probed with several experiments, astroparticle experiments, and everything is driven by the fundamental piece of Lagrangian in which the axion or the ALPS particle is related with the photon and can convert back one into another when interacting into electromagnetic and electromagnetic fields. So, of course, I cannot cover everything, but where high-energy astrophysics is more relevant is here in this ballpark of microelectron volt masses and low couplings. And this is just a summary plot of different constraints, and I will focus on high-energy gamma-ray constraints and X-ray constraints, and then I will finally mention how to use radio wavelengths also for axion dark matter. So just to resume, if you have a monochromatic photon ALPS beam, then you have an interconnection between the photon states and the ALPS states, and the equation of motion can be described with the density matrix formalism, and you have an effective mixing metric where the different terms are explicit here. I don't want you to take any details of that, but just recall that every parameter gets several inputs that leads to the energy dependence and the dependence on the transversal B field, the mass of the axion, and the coupling between the axion and the photon. Whenever we want to study a process in high-energy astrophysics, the main process that has been connected to the axion physics is actually the conversion of a high-energy photon. You can see that in the very top corner, that gets transformed into an axion when in the passing through a magnetic field, and then we have the reconversion again in a magnetic field into photons. And only the transversal component of the magnetic field with respect to the direction of the propagation of the photons is the one that matters in the parametrization. So if you take a single domain over which the magnetic field is actually coherent and homogeneous, and let's say that this magnetic domain has a dimension d, then the problem just reduced to a two-dimensional problem, and you can actually describe the probability of oscillation of the photon into the axion on ALPS particle as you do actually for oscillation of neutrinos, or where you have a mixing angle, and the probability oscillation also depends on the same parameters that describe the equation of motion. And then if you introduce this critical energy, defined here, you can reparameterize this oscillation phase in terms of this critical energy. And this is what matters from a phenomenological point of view, because then you can decouple two different regimes. One, when you have the energy which is much larger than the critical energy, so this is the energy of the photon, then the oscillation wave number does not depend on energy anymore, and you have actually maximal mixing, so you are in the strong mixing regime. On the other hand, if you have a photon that is almost at the critical energy, you have the full oscillatory pattern, and so you can dub it as oscillation regime. Just to see it in a more easy way, so if you have the probability of conversion as a function of energy in arbitrary units, you can see that the critical energy, which is here reparameterized in terms of the different terms that matter, so the coupling, the transversal B field, and the axion mass, then this critical energy really defines the transition between the oscillation regimes, where the probability is negligibly small with respect to the strong mixing regime, but still can lead to spectral features that might be looked for, and the strong mixing regime at high energy, where the probability of conversion is maximal. So these two regimes might lead to two different observables that we can actually target with experiments. So on the one hand, you can look for spectral irregularities at around the critical energies in the spectrum of high energy sources. And on the other hand, you can actually have a way to boost the flux of photons at several wavelengths because axion or axion-like particles do not suffer from propagation effects, as it is the case for high-energy gamma rays. And we will see that in the following. So let's start for spectral irregularities. So, as I said, this phenomenon occurs when the photon has almost the energy of the critical density, and the critical density, reparameterized this way, depends on the one hand on particle physics parameters, so the mass of the axion of the ALPS particle and the coupling of the ALPS and photons, and on the other hand on astrophysical parameters that describe the environment where the transition takes place. So in particular, it depends on the frequency of the plasma, which gives an effective mass to the photons, and depends on the density of electrons in the medium. And as I was saying before, it depends on the transversal component of the magnetic field. So let's just take two examples, just to have an idea of the numbers. So if you take galaxy clusters, in those the energy, the density of electrons is about 10 to the minus 2 centimeters cubed, and the central B field in the core of the cluster can can go up to 10 microgauss and even higher, while in our Milky Way we have an average density of electron of 0.1 centimeters cube, while the B field is suppressed with respect to larger environments and is of the order of 1 microgauss. Those, of course, are average quantities. So if then we look at fixing the photon ALPS coupling to 10 to the minus 11, how the critical energy density, the critical energy changes with the mass of the ALPS, we can see that if we have a mass of the axion in the micro electron volt range, then the critical energy will be around the TeV. And on the other hand, if we have a very small mass, let's say 10 to the minus 12, we are at the keV energies for the critical energy. So if you want to look for spectral features in the spectra of high energy sources, you can probe nano-electron volt masses and micro-electron volt masses with GeV to TeV photons. And if you want to go down in masses, you have actually also to go down in energy of the photons that you are probing.
Sorry to interrupt. So what's the critical energy?
So the critical energy is just a parameter that allows you to discriminate those two regimes. So above the critical energy, the probability of conversion is not dependent anymore on energy.
Is this a reference region, like plasma mass equal to the?
Right. No, it's not really that. So the critical energy is defined here. So yes, you have. Basically, it's given in terms of these terms, and it allows you to rewrite the oscillation phase in terms of the energy of the photon. In such a way, you can actually decouple the energy dependence when the energy of the photon is much larger than the energy of this critical energy. And yes, it is related on the interplay between the plasma frequency and the axion ALPS mass. But it's not exactly when the two are equal. Okay, so then as for the GeV to TeV range, so we have several experiments, gamma ray telescopes that might be space-based, like the Fermi Large Area Telescope, which is a pair conversion telescope that scans the sky since already more than 10 years. And then we have ground-based telescopes that detect photons starting from 100 GeV up to the TeV range, and we have three main operating Cherenkov telescopes, HESS, Magic and Veritas, and then the future planned Cherenkov telescope array. So if you want to study spectral irregularities in the spectrum of high energy sources, what you need are some basic requirements. First of all, you need very bright sources as a target for your search, because you want high statistics in the data points in order to really be able to claim that there is a spectral signature. Then the source should be far enough and along a direction in which you have a strong magnetic field in order to maximize the probability of conversion. And for example, you can choose a source that is behind or within a galaxy cluster where the magnetic field is enhanced. And then, of course, you want to have a target where you have a good knowledge of the magnetic field, because whenever you do ALP searches, you always have this degeneracy between the coupling and the transversal magnetic field. And to break it, you need to have a good handle on what is the magnetic field transversal component. So this is an example of the conversion probability in the Milky Way magnetic field. So I don't know how many of you are familiar with that, but this is a North Sky map in longitude and latitude coordinates. This is the direction of the galactic center, and this corresponds to the disk of the Milky Way. And this is fixing the coupling and the mass to some given value, and using a model for the galactic magnetic field, which is one of the most well-studied ones. And you can see that the probability of conversion actually changes depending on the position in the sky. And so you can actually optimize your selected targets in order to maximize that conversion probability. So I will go through several searches that have been performed. The first one, also chronologically, has been done by the HESS experiment by looking at this very bright AGN and searching. So what you do when you have a gamma ray source is that you measure spectral points. So this is the gamma ray flux as a function of energy, and these are the points that you detect and you analyze with your telescope. And then what you want to do is to look for deviations above a power law of your data point. So if there is a deviation which is significant above a given model, so in this case a power law, then you can claim that there is a spectral feature, so you can study what is the significance, and you can interpret it in terms of a particle physics model, for example. So there was no preference found for oscillations of an ALPS particle into a photon, so the spectra were consistent with the absence of conversion of a photon into ALPS particles. And this is the constraint that has been put in the coupling versus mass plane, where you see that this is at the boundary of the cast limit, so the CERN helioscope. And there are two disconnected regions, because there are two regions that are probed by different magnetic fields. So this is probed by the intergalactic magnetic field, and this is probed actually by the magnetic field in the galaxy cluster, where in the direction of this source. So next, also at GV energy, you can study the oscillations, as I was saying, but you are probing a different range in masses. And what was done by the Fermi-LAT collaboration was to study this radio galaxy, NGC 1275, and testing different hypotheses, so the presence or not of the oscillations. So when you have oscillations, you can actually parameterize the spectrum, convolving it with the probability of survival probability of the photons, so this P gamma gamma. And in the absence of the ALPs-photon coupling, you have actually only the intrinsic spectrum times some attenuation that we will see later how this comes into play. So this is the energy spectrum, again as it was before, as a function of the energy. The black points are the measured spectral points for the source. And you can see two different fits, one with an oscillatory behavior, which is the best fit with the presence of ALPs-photon conversion, and the other one is a smooth, exponentially falling down power law correspond to the absence of ALPs. So there was no preference found for, again, this parameterization to give a better fit than the other, and so upper limits were set on the coupling as a function of mass again. And I believe the test limit is here at the edge of the plot, and the shape of these contours that are actually exclusion lines are determined by the modeling of the magnetic field configurations within the Perseus cluster, because this source is the radio galaxies which is within the Perseus clusters, that is quite uncertain. And above all, also the modelization of the intergalactic.
Sorry, what's the green color code?
The green, where here?
To the left.
So this is this is the likelihood for these spectral points, and you can actually see that it has almost a symmetric behavior with respect to the spectral points. I mean, this is just for reference for the statistical analysis.
So the lighter, of course,
yes. The lighter
is central, basically.
Yes.
Yeah, with respect to the point.
Is -2 log likely. Yeah. So the other thing that you can do, and what we have done in collaboration with Jelik Majumdar and Dieter Horst in Hamburg, was to look to target galactic sources. So not extragalactic ones, but sources that are within our own galaxy, and for which you have a good determination of the distance, and for which you want to maximize the conversion probability. So the first thing was to select a sample of 6 galactic gamma ray sources, which are pulsars. So pulsars are rapidly spinning neutron stars that have been detected since many, many years, both in radio and gamma rays, and for which you have a very good determination of the distance within 20–30%, but this for astrophysics is okay. And you can see that if you want to maximize the probability of conversion, you can look at the projection of the magnetic field configuration onto the galactic plane, where you see the structure of the spiral arcs. And these are the positions of the 6 sources that we have selected, which are characterized by different positions with respect to the spiral arc. So what you can also do is to study how, if any, the conversion probability depends on the fact that different spiral arms have been crossed by the photons during their travel. And then we have also selected one source that is very close, is very bright, and does not show any spectral modulation, which is the Vela pulsar, to actually derive in a data-driven way what are the experimental systematic uncertainties on the spectrum determination, which are about of the order of 3%. So the aim is actually to analyze the spectral energy distribution of the sources and to see if there is any evidence for oscillatory features when the photon travels to the large-scale regular component of the magnetic galactic field. So then for each source, what you do is to derive those black points here, which are again the flux as a function of energy. So the data points are the black ones, and then you actually test several hypotheses. So you do fit with and without ALPS conversion. And what we found is that there is a significant improvement when you add the ALPS conversion. And this is, for example, for this source, which is the one that leads to the better improvement. This is due to this feature at about 3 GeV over there, and to some effect in the tail of the spectrum. So what you do is actually that you have an intrinsic spectrum, which is the spectrum that the source would emit originally, and then you convolve it with the conversion probability, actually, so the survival probability, as it was done for the Fermi analysis. And you test your hypothesis against the null hypothesis of having no oscillations. So you can also see the results here again, which is a scan over the parameter space, the coupling as a function of mass, And you see that you can see the global minimum there, the very dark blue region, and also some feature of the oscillation. So you actually have an oscillatory behavior also in the best fit parameters, which is due to the fact that you are looking for this kind of features. And to understand what happens and why you have these minima, you can look actually at this plot, which is the conversion probability, the survival probability of the photon in this case, and the conversion probability of the atom in this case. As a function of distance, so the Earth is here, the source is located at 10 kiloparsecs, so it's here, while transversing the magnetic field. So the green dashed line is the transversal magnetic field component, so the photon, you start with a fully photon beam, ampularized photon beam, that gets to a depletion of about 60% at Earth, while you start without axions, and it gets converted into photons while it traverses the magnetic field. And again, you have different reconversions, which actually are corresponding to different spiral arms that you are crossing. So the results for these sources is here. You have an improvement in the fit of about 4 sigma, which might be or not significant. But what we did was also to perform actually combined fit, because what you would like to have is just the same mass and coupling combination might explain well all the spectra. And this is not what is happening. So the best fit parameters of the global fit are not consistent with the single best fit parameter for each source. And this gives you an idea that there is still something that might actually alter your results. For example, there are many unknowns. For example, the opening angle between the spiral arms, or the transversal component of the V field itself. Because just to remind you, what we really probe with Faraday rotation, which is the way in which we measure magnetic fields, is not the transversal component, but the longitudinal components of the magnetic field. And so we will actually need a better determination of the galactic magnetic field before claiming that those spectral features are actually due to some effects like ALPs presence. But nevertheless, the presence of spectral variation is at the order of 20–40%, so it's there, against a systematic uncertainty that is of about 3%. And there are theoretical systematic uncertainties, as I was saying, that also are related to the distance of the sources. And last but not least, this region is actually already excluded by the cast limits. So
Could you go please 2 slides back, actually, where you show the fit? Yeah. So that fit shows. So how do you see that the fit improves when you add the ALPs? So I see a cusp structure there. Which the intrinsic fit departs from, no?
Yes, and also a bit here. I mean, there is also some effects of the tails. Then you compute the chi-square, you have 2 degrees of freedom more, and what you do, you can compute the...
So, the physics-wise, the fit with the ALP is H1.
Is H1. So, just to be clear, H0 is the null hypothesis, so without ALPs. H1 is with ALPs only for this source. And H2 is is the with ALPs but for the global fit. So basically correspond to different parameters, photon mass coupling parameters. Because it's when you do the global fit of all the 6 sources together, so you only have 2 free parameters for all the 6 sources. While H1 is when you perform a fit only on the single source.
Yeah. So there is no way the intrinsic fit can actually completely account for this.
No.
I mean, it's the thing is macroscopic.
So there are spectral features in the energy spectrum for these sources. You can also, ideally, you can also do like a model-independent study of those spectral features, and you can quantify how much deviation you have with respect to a smooth function, So we didn't do that. We did a phenomenological study of photon coupling. But it's clear that there are features that might be more or less significant that makes your intrinsic spectrum not to describe properly what you see in the data. And this occurs also for the other sources with less significance. So this is the source that gives you the highest significance. This is also the one that drives the global fit in this region of the parameter space. So, but what I was saying is that if you put things in context, this region is already excluded by the cast limits, as well as it might be in tension with the supernova 1987A limits on the coupling and mass. So there might be, you can actually maybe solve this issue if you take into account plasma effects that are present in the sun but not in the intergalactic medium. But this issue has not been studied yet, so I don't want to speculate too much on this. The results are, however, consistent with the TV transparency lower limit and hints from cyber, which is this pink region, and do not seem too much in contrast with Fermi-Lat and Hess limits. We also tried to understand if there could be some intrinsic effect due to the source itself, so to the physics of the pulsars, but we couldn't find any. And also there is another analysis from Xia collaborators about supernova remnant in the Fermi-Lat catalog that finds actually a best fit region in the same ballpark. So this has still to be settled. So in the last 5 minutes that I have, I will actually go a bit more quicker. And I will just go through the main results, and you're free to ask me if you have more questions. So as I was saying, if you want to probe smaller masses, so 10 to the 13th, 10 to the 12, 10 to the minus 13th, 10 to the minus 12 electron volts, you can use X-rays. And this is what has been done by different authors using different very bright AGN or quasars behind clusters or within galaxy clusters. And no evidence for oscillations was found, and upper limits, which are quite stronger, were set. So the X-ray are actually very well constraining below 10 to the 12 electron volt ALPS masses. Another issue which is still open is the absorption of high energy photons and the opacity of the universe. So what happens when photons at very high energies are emitted from an extragalactic source is that they travel through the intergalactic medium before being detected at Earth, and during this their path, they are actually absorbed by what we call the extragalactic background light, which is the light emitted by all galaxies in the infrared and optical domain that is such that interacting with a very high energy photon can lead to a pair production of E plus, E minus, and therefore deplete the high energy flux of photons that are emitted by the source itself. And what was found by several studies is that the universe is actually more transparent than what is predicted by ABL models. So how to account for that was not clear and can be actually used to probe again axion-like particles. So I will just skip this. The idea is that the conversion of a high energy photons into axion can solve the issue of the transparency of the universe, because actually you have the conversion of photons into axions. The axions travel unperturbed through the intergalactic medium, while the photons are completely absorbed, and then in the galaxy, in our galaxy, the photons get reconverted, the axions get reconverted into photons, and we detect a flux of high energy photons, which is lower than what was in input at the source position, but still higher than what you would have without ALPs-photon conversion. And this is an example for an high energy source. Without ALPs, you have a very soft spectrum. With ALPs, you have a very hard spectrum. And this might actually solve some of the issues that have been seen related to the TV transparency of the universe. And you can use that to set a lower limit on the coupling versus mass. I will just finish maybe here to say that this cosmic ray opacity problem is not actually completely understood because the latest analysis of Fermi-Lat data and high energy S and Cherenkov telescope zeta didn't find any evidence for this reduced cosmic opacity. And so the issue remains to be settled by the next generation of high energy gamma ray telescopes, in particular CTA. So what I wanted to convey here is that you can really use multi-wavelength observation to probe the coupling of axion-like particles with the photon, and that you can get some hints from these very high energy observations that are anyhow challenged by several constraints. And the future of our era is very bright because we will have several experiments at several wavelengths, so SKA in radio, although I didn't have time to talk here about that, Athena in X-ray, and CTA and Oak in the domain of very high energy gamma rays that can really help us to settle some of these issues and further constraints the allowed parameter space. And I just want to conclude with a reminder. So I just want to stress the degeneracy with the B-field configuration, and those experiments will also help in having a better description of this crucial parameter in our universe.
Thank you very much. Questions or comments? So maybe I start with the. So of course I find it very exciting, this hint of an ALP at this mass and the coupling. So the question is, so I mean you found, so to say, somehow all this you could fit this excess at a certain mass. This I find much more exciting than the coupling itself, because the coupling is degenerate with the B field. So the question, and this Chinese group, they found again at the same mass.
Yeah.
So the question for me is now, so isn't it could one somehow try even to fit somehow the magnetic field and to see whether one gets with the magnetic field as a further, or somehow to determine the magnetic field somehow by this observation, because we know at the end, if we know an axion-like particle, if we know its mass, then at the end we can determine magnetic fields much better than the Faraday effect.
Yeah.
So what is
sure.
your...
No, I completely agree. First, you have to be sure that is an ALPS particle there.
But we will see, in 2 years we will know this.
Because anyhow, ALPS should probe that.
ALPS probes this thing in 2 years. ALPS is running light shining to the wall in the laboratory. We have no problem. We know our magnetic field.
But yes, I mean, you can reverse engineer the problem and saying if ALPS are there, if this is actually true spectral features due to this conversion.
I found this exciting because you always find the same mass.
Yes, they are all in the same ballpark, and there is also this Chinese group that find the same. But what actually you can also do is to add more parameters to your fit and to vary also the B field simultaneously with your particle physics parameters. And actually you find that you can get a bit lower coupling by doing so, but then the data, I mean radio data and polarization Planck data are not yet telling you if what you find is reasonable or not. So for now you can do some phenomenological study of what you would get. Sure.
But how many pulsars are there still? Which
Okay, the sample of pulsars that has been detected in gamma ray is about 130 sources. But then you have to cope with the fact that not all of them are very bright. So you need, as I was saying, high statistics for the spectral analysis. Otherwise, you cannot really study the variations. And also they have to be at low latitudes in order for the photons to cross spiral arms. Otherwise, you will basically lose any information on the transversal component of the B field. So I think you can still select quite a few, let's say tens of them, that might be worth analyzing in order to see if there is again some region of the parameter space in common.
So when you floated the magnetic field, the compatibility of the sources was, the masses were compatible?
It gets better, yes.
In the mass?
In the coupling. And the mass a bit, but not too much. So it's really the coupling that makes the difference. But then you don't have any way to say, this is the right configuration of the magnetic field, because the constraints that are on the market are not very strong.
How incompatible are these sources?
I think there are less, let's say, less than 3 sigma incompatibility for the masses, while the couplings are better in agreement. We have the table, but I didn't put that in the backup slide.
Other questions?
So this less than 3 sigma means
Is
it
that
would increase if you had more sources. I mean, how it's this? How is the chi-square normal? I don't know what to ask exactly.
So the meaning of 4.6 sigma was between what?
is the global evidence of the global fit.
So this was between H1 and H2.
H2, H0.
Yeah,
H2,
H0.
H0. Is 5.5 is you do H1 and H0. What you are, you are kind of interested in the global fit, but also you don't have to take it too strictly, because again, there might be mismodeling of the magnetic field that you are not accounting for. So it's something in between.
Transversal component, how is it calculated? Is that the same value as the longitudinal ones, or there are some models?
There are models for that. So these Jensen and Farrar models also have some way to they project and to get the transversal component of the B field. Then using the polarization, the Planck polarization, there was actually an update of this model that we use, in which you get a better constraining on the transversal part. But still, you need more to collect more data and to run better analysis on that.
Okay, so thank you very much, Francesca.